In this video, we're going to look at the structure of a beta turn. So there are a number of turns that are stabilized by hydrogen bonding to allow for changing the direction of the peptide backbone. Okay, so for instance, to make a pleated sheet, so a beta sheet, right? Uh, there are several strands. There's several changes in direction that are required in order to make that sheet, right? So that sort of crisscrosses back and forth with each other. So they can continue to make hydrogen bond interactings with strands that stabilize that secondary structural motif. So sometimes these turns, okay, are used in order to facilitate that. So this is one type of turn, so that requires four amino acids to be connected. So these are the alpha carbons that are listed. So this is a type 1 and a type 2, and there's a difference in orientation of the peptide bonds and also the distances. But the important thing is to understand how this motif is stabilized. So there are four alpha carbons listed, 1, 2, 3, and 4. Okay, and there are three peptide bonds in this picture. So one here, a second one here, and a third one here. Okay, what you'll notice is that these orient in such a way in order to make a very sharp turn. Okay, another key to this is that these beta turns are typically have glycines in them in order to facilitate because of the small because that's the smallest side chain that allows for these very small turns to occur with a minimum number of amino acids. Okay, so four amino acids here, and then what happens is there's a stabilization of the peptide bond, or excuse me, the turn, using the NH of the N+3 residue and the CO of the N residue shown here. So this has an H bond interaction that stabilizes the turn and also allows that to be a sharper turn to a sharper turn using a minimal amount of amino acids.